Why direct injection is slowly suffocating your engine. The $1,500 carbon trap. You buy a modern car. You are thrilled with the performance. It has excellent horsepower, instantaneous throttle response, and fantastic fuel economy. The dealership proudly tells you it is equipped with a state-of-the-art direct injection engine. You drive it for 50,000 miles, taking good care of it. But then, something changes. The car starts to idle roughly at stoplights. The engine vibrates nervously. When you step on the gas to merge onto the highway, it hesitates. It feels sluggish, like it is struggling to breathe. Your fuel economy drops by 20%. Eventually, the dreaded check engine light flashes on your dashboard, warning you of multiple cylinder misfires. You take it to a specialized mechanic. They insert a tiny borescope camera deep into your engine's intake manifold. What they show you on the screen is terrifying. The internal breathing passages of your engine are heavily clogged with thick, black, hardened rock-like formations. The mechanic hands you an estimate for $1,500 for a procedure called walnut blasting. You ask if you can just pour a bottle of fuel cleaner in the gas tank. The mechanic shakes his head and says, "That won't touch it." The fuel never reaches this part of the engine anymore. If you want to understand how modern engineering is slowly suffocating your engine and how to prevent this massive repair bill, keep watching. To understand the magnitude of this $1,500 engineering trap, we have to travel back in time and look at how engines used to be built. For decades, the automotive industry relied on a system called port fuel injection. In a port-injected engine, the fuel injector is located inside the intake manifold, positioned just slightly upstream from the intake valve. When the engine's computer commands fuel, the injector sprays a fine mist of gasoline into the incoming stream of fresh air. This air-fuel mixture then flows past the intake valve and into the combustion chamber to be ignited. This design had a massive, unintended mechanical benefit. Gasoline is not just a highly combustible fuel, it is also a highly effective chemical solvent. Furthermore, federal regulations require all gasoline to contain powerful chemical detergents. In a port-injected engine, every single time the injector fires, that powerful, detergent-rich gasoline washes directly over the backside of the hot intake valve. Millions of times over the lifespan of the car, the valve is constantly being power washed by the fuel. Because of this constant chemical cleaning, the intake valves in older port-injected engines remained remarkably clean and shiny, even after 200,000 miles. But in the relentless pursuit of better fuel economy and lower emissions to meet strict government regulations, engineers had to make a change. They introduced gasoline direct injection, commonly known as GDI. In a direct injection engine, engineers took the fuel injector out of the intake manifold and moved it directly into the combustion chamber, right next to the spark plug. Instead of spraying fuel at 50 or 60 pounds per square inch, these new ultra-high-pressure injectors blast fuel directly into the cylinder at pressures often reaching 2,000 to 3,000 psi. The benefits of this are undeniable. The high-pressure spray creates a much finer atomization of the fuel. Spraying fuel directly into the cylinder dramatically cools the combustion chamber, allowing engineers to raise the engine's compression ratio without causing dangerous engine knock. Higher compression means more horsepower and better miles per gallon from a smaller engine. On paper and in the showroom, direct injection is a masterpiece of modern engineering. However, moving the fuel injector created a massive, catastrophic vulnerability. By putting the injector inside the cylinder, there is no longer any fuel flowing past the backside of the intake valve. The intake valve is now completely dry. It receives air and nothing but air. You might be thinking, if it's just fresh air passing over the valve, why would it get dirty? And that brings us back to the silent killer we exposed in our previous video, the PCV system, now often joined by exhaust gas recirculation. As we learned, the positive crankcase ventilation system routes hot, oily, acidic blow-by gases out of the crankcase and dumps them right back into the engine's intake manifold. Many modern engines also use exhaust gas recirculation, or EGR, which sends hot, soot-filled exhaust back into the intake to reduce combustion temperatures. In the old port-injected engines, this mixture of oily PCV vapor and EGR soot would flow past the intake valves, but the constant spray of detergent gasoline would immediately wash the contaminants away before they could stick. In a direct injection engine, that washing mechanism is gone. Now, you have a steady stream of hot, oily vapor and abrasive soot blowing directly onto a dry, bare steel intake valve. The intake valve is extremely hot, often operating at hundreds of degrees Fahrenheit. When this cocktail of oil, water vapor, and combustion byproducts hit the scorching hot metal of the valve, they do not just sit there. They bake. The heat triggers a chemical reaction called coking. The liquid vaporizes, leaving behind a hard, carbonized, rock-like deposit permanently bonded to the metal. This is not a defect. It is a fundamental chemical consequence of the GDI engine design. As you drive your car for 30,000, 50,000, or 80,000 miles, this coking process continues endlessly. Layer upon layer of dense, black carbon builds up on the neck and the face of the intake valves. It looks exactly like heavy cholesterol building up inside a human artery. As the carbon deposit grows thicker, it begins to physically choke the engine. Engines are essentially giant air pumps. To make power, they need to breathe freely. The engineers designed the intake ports with incredible precision to create a specific tumble or swirl effect in the airflow, maximizing combustion efficiency. When massive chunks of jagged carbon obstruct the valve, that aerodynamic swirl is completely destroyed. The engine physically cannot pull in enough air. This restricted, turbulent airflow causes the engine to run lean, misfire, and lose volumetric efficiency. The computer desperately tries to compensate by altering ignition timing and dumping more fuel into the cylinder, entirely negating the fuel economy benefits you bought the car for in the first place. The engine vibrates, hesitates, and slowly suffocates. So how do you fix it? This is where the marketing industry misleads millions of GDI owners. You go to an auto parts store, and you see shelves lined with expensive fuel injector cleaners and complete fuel system treatments. The bottle promises to restore lost power and clean your valves. You pour it into your gas tank, hoping for a miracle. It is largely ineffective against this specific problem. Remember the architecture of the GDI engine. The fuel from the gas tank goes straight into the combustion chamber. It physically never touches the backside of the intake valves where the carbon is building up. You are treating a symptom in the wrong part of the body. Chemical additives in the fuel tank cannot clean what the fuel never touches. The only effective way to cure a suffocating direct injection engine is a labor-intensive physical intervention. The industry standard procedure is called walnut blasting. A mechanic must physically remove the entire intake manifold from the engine block, exposing the heavily carbonized valves. They cannot just scrape the carbon off with a metal screwdriver, because scratching the precisely machined aluminum cylinder head or the valve stem would destroy the engine's compression. Instead, They use a specialized pressurized blasting machine. But they do not use sand or glass beads, because that media would destroy the metal internals. They use crushed organic walnut shells. Walnut shells are a mild organic abrasive. They are hard enough to shatter and strip away the baked-on carbon deposits, but soft enough that they will not scratch the aluminum cylinder head or the steel valves. The mechanic uses a high-powered vacuum to suck out the pulverized carbon and walnut shells simultaneously. They must repeat this meticulous process for every single cylinder. Because it requires significant disassembly and specialized equipment, this procedure regularly costs between $1,000 and $1,500. So what is the survival protocol? If you own a modern vehicle, you likely have a direct injection engine. How do you delay or prevent this $1,500 carbon tax? Here are the 3 actionable, engineering-based steps you must take. Rule number 1. You must upgrade to low NOAC volatility engine oil. This is the most critical technical defense you have. While carbon buildup has complex origins, it comes primarily from oil vapor and combustion byproducts turning into a vapor through the PCV system. Not all synthetic oils are created equal. NOAC volatility is an industry-standard test that measures exactly how much a specific motor oil evaporates and turns into vapor at high temperatures. Cheap, generic synthetic oils often have a high NOAC percentage, meaning they vaporize easily, sending massive amounts of oil mist directly to your intake valves. High-quality, premium full synthetic oils are engineered with a much lower NOAC volatility score. By spending a little more on premium oil, you drastically reduce the amount of oil vapor passing through the PCV system, starving the carbon buildup of its primary fuel source. Rule number 2. Shorten your oil change intervals immediately. As engine oil ages, its chemical stability breaks down, and it becomes much more prone to vaporization under high temperatures. Oil that has been in your engine for 8,000 miles vaporizes more easily, massively increasing the oily vapor entering the PCV system compared to fresh oil. Changing your premium synthetic oil every 5,000 miles ensures the oil remains chemically stable, further reducing the vapors that cause valve coking. Clean oil is the shield that protects modern, high-tech engines. Rule number 3. Consider a preventative chemical induction service, not a fuel additive. While fuel tank additives are ineffective, there are specific GDI cleaning sprays. These chemicals are not poured into the gas tank. They are sprayed directly into the engine's air intake manifold while the engine is running. This allows the powerful chemical solvents to physically flow over the backside of the valves. However, you must understand the limitation. If your valves already have 80,000 miles of hardened, rock-solid carbon, a spray will not fix it. You need the walnut blasting. These chemical sprays are strictly preventative. If performed by a professional every 20,000 to 30,000 miles from when the car is relatively new, it can dissolve the soft, newly formed oil deposits before they have a chance to bake into hard carbon rocks. To summarize the engineering reality of modern driving, progress always comes with a hidden cost. Direct injection gives you more power and better fuel economy, but it sacrificed the vital chemical cleaning of the intake valves. Fuel tank additives are a marketing illusion for this specific, suffocating problem. Ignoring oil quality and maintenance intervals accelerates the choking of your engine, leading directly to a $1,500 physical repair. Do not let your engine choke to death on its own vapors. Next time, we are going to expose another modern feature designed to save you a few pennies on gas, while secretly destroying your engine's bearings and costing you a fortune in electrical repairs. We will reveal the destructive engineering truth behind the auto start-stop system and why you should press that disable button every single time you start your car. Subscribe if you want to understand the engineering realities of your vehicle and how to protect it from the dealership's profit-driven maintenance schedules.